we don't normally introduce our seminar speakers. They just drift up to the front, speak, and drift away again. But since Steve's come all this way just to give a seminar, I think we should do the least introduce you properly. So we're very pleased to have Steve Baldwin with us to talk about the iso rotation contours in the sun. Is that
Isotax, right.
yes, right? And many of you will know his work in accretion disks and stability of accretion disks. The so-called MRI problem is very well known and very important. But he's worked on many other things as well, as we're just about to discover. MIT originally, I think, and then off to Virginia Tech. And after 20 years there, I missed that. Princeton.
I lost my whole career. So. Berkeley, Princeton, and University of Virginia.
Anyway, eventually Virginia Tech. After 20 years, he decided he didn't like it. And now he's in Paris, lucky man. I think that's all.
Exactly. It's the civilized part of the world. Talk so. So I want to thank Peter for the invitation to come and present here. I'm delighted to be here. As Peter suggested, most of my research effort in the last many years has been centered around accretion disks and so occasional work on dilute plasmas. I feel very much a newcomer to the field of solar physics, and I'm a little daunted speaking before an audience at Cambridge where in fact there's a great deal of expertise on the topic. So I enter into this field a bit as an outsider. So if I seem a little bit naive, please bear with me. But I would like to show you kind of what seems to me an interesting and promising route to understanding why the sun rotates the way that it does. So I guess the audience here consists of, I can see a lot of friendly faces, so I know there's some astrophysicists, and then some who are coming from the more formal turbulence school. So let me take just a moment to set up the problem. And that is that I think in most astrophysicists' opinion, one of the most beautiful astronomical results of the last half century was the precision determination of the interior solar rotation, a real tour de force of astronomical and mathematical technique. Basically, the idea is that by looking at the oscillation, the external oscillations of the sun, so-called P modes, modes that are pressure-driven and result in oscillations of the surface, this allows an accurate determination of the interior rotation profile, because the effect of the rotation is to cause slight frequency shifts in the P modes over what they would have been without the rotation. And it's possible to invert that problem by looking at the frequency of the excited modes and then work out in detail what was the rotation profile that gave rise to the particular spectrum of excited modes that are seen. A very difficult and beautifully done problem, and a lot of that work was done here. Basic findings are very surprising, very interesting. The only place in the sun where there is significant differential rotation is in the convective zone. As far as we know, the radiative zone of the sun. I should maybe just take a second to explain the sun. So there's a core region where the nuclear reactions occur, a radiative zone, so-called radiative zone, where the radiation is diffused and the luminosity kind of leaks out very slowly. And then the outer layers are convectively unstable, and the primary energy transport is by large-scale mechanical convective motions. So that's the place where the sun is grossly turbulent. It's also the place where you see any significant differential rotation. The radiative zone is, as far as we can tell, very nearly in solid body rotation. In accretion disk models, a popular way of describing the effects of the rotation has been as an enhanced, the effects of the turbulence has been as an enhanced viscosity. Well, in the sun, that would fail miserably. The only place where you supposedly have this gigantic viscosity happens to be the place where you have differential rotation and no other place, so it gets the sign completely wrong. So the rotation profile is approximately constant on cones of constant theta at mid-latitudes. You saw the picture in the very beginning of the talk. I'll come back to it several times. The rotation contours near the equator are cylindrical, and near the poles they tend to follow spherical surfaces. So here's the picture, data taken from Howe et al. 2000. The work...
There's a pointer in the corner there.
Right, all right. So the work on this, the early data sort of is from the mid-1980s. And so by now it's been highly refined, and everybody, I think, basically agrees on the overall organization of the rotation. So this is data taken from Howe et al. And one of the features which is fascinating to many fluid dynamicists following this problem is the so-called tachocline. And as the name suggests, it's a region where the rotation velocity changes dramatically, particularly near the polar regions of the sun, although it extends quite a bit far down, perhaps 40 degrees or so. And it seems to be some kind of a boundary layer phenomenon between the solid body rotation and the differential rotation in the convective zone. And that is probably, I use the word boundary layer specifically and intentionally because that is probably a region where the dominant physics changes. I'll discuss what I think, and what I think most people agree on is kind of the dominant force balance in the convective zone. The tachocline region itself is probably, well, it certainly is much more complex and the subject of intense investigations by many groups around the world, and one of the experts here, as you probably know, is Professor McIntyre. There is also things change when you get very near the surface and the convective motions become very, very large. Within the bulk of the convective zone, the actual convective motions are relatively small, 10, 20, 30 meters per second. An Olympic runner could almost outrun the slowest convective motions. But near the surface, they can become quite pronounced. They can approach the speed of sound in some cases. And in fact, there's significant shear going on near the surface layers. So what I will discuss today shouldn't really directly apply to the surface, and it won't apply to the tachocline, but I do expect it to apply to the bulk of the interior of the convective zone. Well, the fundamental problem is that the convective zone is very nearly adiabatic. It's convective because the entropy decreases outward, and the first thing that the gas wants to do is to try to eliminate that gradient. And so to first order, P goes like rho to the 5/3. It's an adiabatic barotropic equation of state. The convective motions, as I've indicated, except near the surface, are very small, typically not more than 30 meters per second. And a barotropic fluid, so they don't profoundly affect the hydrostatic equilibrium, and a barotropic fluid in hydrostatic equilibrium must rotate on cylinders, basically a variant of the Taylor-Proudman theorem, these known as Taylor columns. The solar rotation profile, as we've seen, is decidedly not constant on cylinders, but large-scale numerical simulations have had a problem for many years trying to avoid these Taylor columns, and they tend to produce, you can't really see the details here, but the colors are very telling. I guess one of the leading groups is the Colorado group. Sasha Brown and Yuri Tumri have been working on this for a number of years. And I think things are starting to get a little bit more presentable, but you can see the general trend here. The contours that the numerical simulations find tend to look much too cylindrical compared to to what the helioseismology data shows.
Is that one on the right, the one where they impose a temperature gradient at the bottom?
I think that's where they impose, yes, a latitudinal entropy gradient.
That's the way they get it looking a bit more.
So they get it look more presentable. They put it in by hand. Yeah.
Sort of like to get the monsoons right in India, you have to increase the temperature, sea surface temperature odd difference by a factor of 2.
Okay, I see this technique then has a noble heritage. Yes. So what is the orthodox view of this problem? And I think this is a fair summary. Despite the simple regularity of the rotation pattern, the flow is really an extremely complex interplay between convective turbulence and rotation. And it really needs, it's not something that one can make progress with analytically. The turbulent convection and the combination of rotation really necessitates a powerful numerical approach. But even within the orthodox view, they will agree that some handles on the problem do exist. There should be a departure from strictly barotropic structure because Coriolis forces affect the convection. If I have Coriolis motion in a plane of constant z, then those motions tend to get deflected. It's harder for a rising parcel near the equator to make it out to near the surface, whereas a parcel rising along the rotation axis is much less impeded. So the idea is that the poles should be relatively hot. The effective thermal conduction is better in that direction than it is tangentially. So we expect, in this picture, hotter poles and cooler equators. Yes?
I never quite understood that argument, though, because near the equator you can convect in a quasi-two-dimensional way, which Yuri Tomry calls his bananas. And that's not specially inhibited by rotation, is it?
No, but I think the route between the sort of the hot interior and the outer layers near the equator cause a diversion that along the lines that you're suggesting, which you don't have. It's simply a much more, I think even in the picture you're describing, it's more efficient to go along the axis than it is to try to fight your way with secondary circulation along the equator.
Go along the axis, you've got to converge down here and diverge up there, and the rotation tends to inhibit that.
Well, I don't know. It strikes me as not implausible that it would that you get a gradient from the poles to the equator, but I agree it's not. There may be ways around it. In any event, it is part of the common folklore.
So that's what's found numerically, I suppose, if you get a hot pole.
I think that's also found numerically as well, but I think that that's the way it's understood. It's basically Coriolis inhibition.
Do we know that for the real sun? Do we know the temperature well enough on the real sun?
Oh, I'm sure not. I don't know that, but I would be astonished. We're talking about temperature differences of a few degrees Kelvin on a background of 3 million, so I'm sure that this is purely theoretical. So this can also be seen more quantitatively in what is known as the thermal wind equation. The thermal wind equation in this context is simply the vorticity equation. This is the azimuthal component of the vorticity equation. And I want to take a second to look at that in some detail because it's going to play an important role in what I'm going to describe. So if I write down, this is essentially the vorticity equation, and I'm already making an important assumption here, and that is I am ignoring the effect of turbulent transport. I'm assuming that the principal motion of the sun is the large-scale differential rotation. I'm ignoring terms of order v over L squared, where v is a turbulent velocity, L is kind of an effective mixing length. That's probably not a bad approximation, but it's also fuzzy. And when thermal wind balance breaks down, as it does in some parts of the convective zone, that is probably one of the primary reasons. But for the bulk of the convective zone, let us assume that we have a balance between the simple z gradients of the angular velocity and this cross product of the pressure and the density. You see, by the way, of course, when P is a function of rho, you immediately find the result that the rotation profile rotates on cylinders. I'll use alternately in the talk either cylindrical coordinates. I'll use an uppercase R, phi, and Z. For cylindrical variables, R, phi, and I'm sorry, this is cylindrical and this is spherical. R, theta, and phi. Theta is colatitude measured down from the z-axis. So if I expand this equation and I write the cross product, so I keep the z dependence on this side of the equation, and I use spherical coordinates on the right side of the equation. I get a term that looks like this, or rather a development that looks like this. And then if I replace the pressure, if I express the pressure in terms of the entropy, and you'll see why I want to do that in just a moment, then that's very easy to do. Obviously, any terms in the pressure that involve, how do I want to say this? If I substitute the entropy for, I borrow one of the rows and make this a log row and then a P, then perhaps if I start with this equation, plug back this expression then for the pressure and the density for the entropy, I find that in fact I get a cancellation between any terms that involved a pressure gradient here and a pressure gradient here because of the symmetry of the equation, and the density terms take me back to this equation. So the point is, there's obviously some freedom in terms of what variables you want to use for the right-hand side of this equation. And it's much more convenient in this problem to substitute instead of the density to express it in a form using the entropy. And then the final step here is to notice that the radial pressure gradient is simply the gravitational force, or 1 over rho times the gravitational force. And that in the sun will greatly exceed the theta gradient, the angular gradient there. The sun is, of course, very nearly round. And as long as this entropy term is not significantly larger than the theta entropy term, and we'll see, in fact, it's probably the case that the opposite is true. But assuming that is okay, we can drop this term relative to the second term, and we wind up with a rather simple equation for the angular velocity gradients in the z direction in terms of the entropy gradients in the theta direction. Cp here is, here it is. It's simply, this K is the Boltzmann constant. It's the heat capacity at constant pressure. And R, of course, this R, remember, is cylindrical R. This R is spherical R.
So that R is cylindrical R and R.
Capital R is cylindrical R, always.
Okay, so the
Lowercase r is always spherical R. And phi is, of course, tends to increase in the opposite direction that z does. So as the entropy, if I head in the direction, say, where the entropy is increasing, that corresponds to a decreasing omega squared. The trend is moving polewards. Omega tends to decrease, whereas the entropy tends to increase. And that's also reflected in the thermal wind equation. So let's put in some numbers to get a sense of the lay of the land. A standard exercise that essentially all students of astrophysics go through at some point when they learn about stellar structure and convective zones is to get an estimate on the entropy gradient, or usually it's in the form of the departure of the temperature profile from a strictly adiabatic temperature profile that is required in order for the solar convection to transport the entire solar luminosity. And this is done, I guess, never more clearly than in Schwarzschild's book from 50 years ago. And one can estimate fairly straightforwardly, using this prescription, a value of n squared, the Brunt-Weisel frequency. I'm writing it in terms of absolute value because it's a frequency, of course, only if the entropy is increasing outwards. In the convective zone, it tends to be decreasing outwards. But this is the numerical value that you get from using such a procedure. Now, when I was a student, it never dawned on me that I should worry about the theta gradient of the entropy. Why would I care about that? The sun is radial. Seems like a waste of time. But in fact, the theta gradient can be estimated by completely different physics. It's interesting. The argument that you can now use to look at what the theta gradient of the entropy, it follows directly from this thermal wind equation that I've just put up, because we can sort of look at the answer in the back of the book. We can look and we see what nature has told us the angular velocity profile inside the sun is. And if the thermal wind equation is valid, and we can read off what omega as a function of r and theta is, then we can directly estimate what the theta gradient of the entropy is. And it's an order of magnitude larger, factor of 5.
Theta gradient is the azimuth?
No, theta is colatitude.
Colatitude.
Yeah. So phi, nothing depends upon phi. Phi is the azimuthal angle in this sense.
Phi is the azimuthal angle.
Yeah, let me just put it up on the board.
This is the thermal wind equation, is that the vertical, the azimuthal, sorry.
So there's theta, and there's
polar.
r, and phi is into the blackboard.
Right, okay.
Okay? Standard spherical coordinate system. So the theta gradient of the entropy exceeds the radial gradient by a factor of something like 5 or so. Maybe it's 3, but maybe it's 15. There's a big difference if the thermal wind balance is in fact a valid concept. So that's interesting. That may be telling us something. Here's another look at the solar isorotation contours. And I've put the gradient of omega explicitly. I picked a sort of place at random and slapped down the omega gradient, and I put in the radial unit vector as a way to guide the eye. And then as best as I could, using the PowerPoint tools, put in an entropy gradient which has this aspect ratio, a theta gradient exceeding by a factor of 5 or so the radial. So this is interesting. These are very nearly counter-aligned. So I want to propose the following at the moment just as an exercise. Let's ask the question, what if the gradient of omega and the gradient of the entropy are more closely related than just the general trend that one tends to go up as the other tends to go down? What if, in fact, as this picture is suggesting, the surfaces of constant omega and the surfaces of constant entropy, in fact, very nearly coincide? One is going up, the other is going down, but the surfaces on which they're constant, what can we learn by this assumption, apparently supported by the data, that there seems to be this close relationship between the entropy and the angular velocity? Well, the nice thing that would happen under those circumstances is that the thermal wind equation would suddenly become a self-contained quasi-linear partial differential equation, the solution of which would essentially give us these isorotational surfaces. So this is what the thermal wind equation looks like under the assumption that the entropy is a function only of omega squared. So I've essentially taken the equation you just saw written the z gradient in terms of spherical coordinates, and then assumed that the entropy was in fact a function only of omega squared. And this is the resulting form of the equation where z prime now represents the derivative of the entropy with respect to the angular velocity surfaces. Now, the solution to this partial differential equation can be solved, it can be found using standard techniques. The solution is that omega squared is constant along the characteristic d theta dr is, as you see here. It's important to note, since we are looking at a contour along which omega is constant, this also means that s primed, which is a function of omega, is also a constant. So I have a differential equation, an ordinary differential equation in theta and r, and then a function of theta and r on the right side. That looks a little bit messy at first, but in fact, it has a very gratifying simplification. If we solve for y equals sine theta, this thing turns out to be simply a first-order linear equation in y squared. And that means we can easily solve for these isorotation contours explicitly. And the solution that you find is that r squared, here's my cylindrical r, which is spherical r squared sine squared theta, is some constant a, an integration constant, minus b over r, where b is a quantity which is made up of kind of fundamental constants, and it depends upon specifically what the function s prime is. But for a given contour, s prime is simply a constant. Typically, you can estimate the b over r cubed is a dimensionless quantity, and if I substitute a value of the solar radius and take a representative value of s prime from the estimates which I gave earlier, then b over r cubed is of order unity or less. That's the number which is kind of near 1 in this argument. Well, already you can start to see that good things are going to happen, at least in terms of fitting the data. When cylindrical r is very small, which it will be when you get near the poles, then this term will be small compared to the right-hand side, in which case what this is telling me is that the contour will be defined by spherical r as a constant, which is just what you saw. You tended to get spherical surfaces when you were near the pole. On the other hand, if I go to a regime where r is getting bigger, where both r's are getting bigger near the equator, so that r, this big R and little r are getting comparable, this term is dropping in importance relative to this term, which is going up quadratically, and so that near the equator, I'm going to get contours that look more cylindrical, which is, again, just what is seen. So without doing any fitting, it at least has the right qualitative behavior. So if we want to get a precise model for omega, what we need to do is we need to pick some location where we agree to fit the data. And the easiest thing for me to do at this stage, although probably not the best physically, but the easy way out is simply to take the surface fit to omega that's been around for many years, use that as my starting point, and then construct my solution characteristics from that point. That's probably not going to display the results to best effect, because the surface layers, we've argued, are affected by rather strong shear. So I'm probably starting off in a region where the thermal wind equation is not a wonderful approximation. I can probably do better. But this was the easy way to begin, and I hope to convince you that, in fact, things don't look too bad at all, even if I fit it to the surface. what you'll see in just a moment is that the kind of contours that appear, they kind of remind me of Batman. They look like Batman contours. So you see the peak here, and then there's a rapid shoot up. This part is actually spurious. It's just it's an extra root, which doesn't make a physical sense.
Okay, that's a different Y than before, isn't it?
Yes, I'm sorry.
That's like Z or the axial.
I should use a different notation. This is Cartesian X and Cartesian Y. Yeah, so this is just what you see is what you get. Then there's a sharp upturn from where I go to the sort of spherical part of the solution to the more cylindrical part of the solution. And remember, when I look at this through the slot of the convective zone, then I may see just this portion, or I may see just this portion, depending upon the actual parameters of the contour. And that's a rather complicated looking contour, I think, for such a simple theory. It's to have it bow down and then move sharply up is a really, for me, this was a very distinctive signature that we're on the right track. So here are various fits. The white circles indicate the standard outline of, or the standard boundaries of the convective zone. And the values that you see here for this 0.1, 0.2, 0.3, 0.4, et cetera, are for B over R cubed, which was essentially the dimensionless value of the entropy gradient, put in, as I say, framed in such a way that it's non-dimensional. And you see that at very low values, things look very cylindrical, but that as I move out to progressively more greater and greater values for this B over R cubed, that I start to get something which is starting to look more like the solar contours that are seen in the helioseismology data. For this very simple model, where I'm assuming, I should also point out, of course, in general, this B parameter, S primed, is something that will change from one contour to another. Here, in what I'm showing you, I'm just assuming that it's the same value on all contours. There's no reason why it should behave in that simple a way, but it's the easiest sort of mathematical problem to do first. I'll show you in just a moment what you can do if you get a slightly more sophisticated. One can also play the same game just as a point of comparison, supposing that, and you might expect this would be the case if you just thought about, well, I don't want to get too far ahead of myself. Let me just say, let's assume, just as a mathematical exercise for the moment, that surfaces of constant entropy and surfaces of angular momentum, rather than angular velocity, coincided. Then it is possible to play exactly the same type of game. You can derive this quasi-linear equation for the angular momentum contours of constant angular momentum. The solution for the characteristic is again solvable by the same types of techniques. You can reduce it to a linear equation for some power of r sine theta. And you get a very different looking equation for the contours. And this is what the constant angular momentum contours tend to look like. They are much more cylindrical. This number indicates the dimensionless value of the entropy gradient now with respect to L squared. And by the time you get up to 0.4, you're getting to see kind of highly distorted contours out here, while you still remain tightly cylindrical near the pole.
This is a different parameter. You were doing this B over whatever before.
It's essentially the same parameter. It's the dimensionless parameter, which is proportional to the entropy gradient. But technically, it's mathematically not the same parameter, but it is the natural dimensionless form of that.
Did you write on the board this one and the other one?
Well,
so we have reference when you flip through your PowerPoint slide.
Sure, it's actually on the slide itself. So,
Oh.
yeah. So here is this value of B.
Yeah.
The real point is it's a
And
completely different equation for the contour shape.
it's a completely different,
Because
yeah.
angular momentum is so different from angular velocity.
So that actually looks the same. The point is they scale. The dimensionless form, one is, I think, the angular velocity, b over r cubed, is dimensionless, whereas in the angular momentum, b times, how would it be? B over r. In other words, I would need to have the dimensionless form would be b over b times r would be dimensionless. I need to take b, multiply it by r. So if I take this r squared, multiply it by
I can't see where you're pointing.
a common error, sorry. If I multiply this r squared over here, then you see the b over r times r squared. B over r is a dimensionless quantity. In this case, b over r cubed was the dimensionless quantity in the other
So
case.
in this case, you have a B, which is G solar mass
Yeah, it's actually,
times S L squared.
yeah, that's the derivative with respect to L squared. The other S prime was the derivative with respect to omega squared.
Okay, so that's the only change, is how the derivative of the entropy.
Well, the dimensionless quantity depends in a different way as well. But it's self-contained within.
But the real point is the left-hand side of that equation has spherical r squared in the denominator.
Absolutely,
Whereas
yeah.
before you had it in the numerator, so it's simply a totally different shape of curve.
That's right. It's less important exactly what the value of b is, as Mike is saying, that the curves themselves don't look anything like the data, whereas the angular velocity curves resemble the data in a way which I find
Oh, I see. So
really
now you've
striking.
taken a different type of B, a different type of balance, and you get curves that don't agree with the data, whereas.
Oh, yes, I'm sorry, maybe I should have picked up on that. That's exactly the point, that the angular velocity curves had a, not 1 over r squared, but r squared, and they had a minus sign over here. So the shape was utterly different regardless of what the value of b is. They just don't look anything like the data. The data really do, in other words, it's not just something which is insensitive if the entropy, goes in kind of the opposite way. You can either use angular velocity or angular momentum. It cares very much that it's angular
What is
velocity.
capital L?
Capital L is specific angular momentum.
Specific angular.
Yeah, this L and, so this L is,
Mass.
and this L, yeah.
Per unit.
I didn't have, this L and this L are
So
the
one
same.
was angular velocity, now is
Angular momentum.
momentum per unit mass.
Yeah, that's right. That's
Okay.
right. One is, r squared omega and omega. And here's a fit, which is rather striking. This is now back to the good solutions with the angular velocity. And this is one where I allow the constant b to vary from one contour to another. And once again, of course, I have fit this to the surface. But you see, it's a little bit hard. The contrast here with black on blue is hard to see. But I have my spherical, almost parabolic contours near the pole. And then the interesting bit appears for just outside the nominal convection zone, in this case, which looks like a problem. I think it's not a huge problem, simply because I'm wagging the dog by the tail here. I'm fitting to the sort of crummy angular velocity, crummy in the sense that it's not really representative of thermal wind balance, but I'm fitting here, and then everything tends to converge at around a value of 0.6 instead of 0.7. But what strikes me about this overall is that I'm getting a tight bunching of the contours here, which looks reminiscent at least of the outer tachocline solution. So it may be that, although I don't want to, at this point, I would certainly not want to push this technique too hard down through the tachocline into the radiative zone, at least as sort of an outer solution. It appears that you can make the contours more tight as you approach the poles here, the radiative zone, by allowing B to vary slightly from one contour to another.
What motivated this shape for the varying of the?
I just, nothing in particular. There's no physics in terms of choosing it. I wanted to see whether it was possible to choose some values that were close to the data. And the answer is that apparently yes, modulo this thing that it's a little bit below the cellar. point of comparison here is a radial line. And so you can see these are strikingly straight, I find, in a way that's quite reminiscent of the data. But they are not exactly radial. Instead, they seem to be displaced parallel to one another, which is in fact a closer representation, I think, to what the data actually show compared to what people say, which is that omega is a function of theta. It's not really a function of theta. It's actually, I think, somewhat closer to this. The contours look like they are parallel displacements. So, why? Why does this work as well as it does? Well, I can remember as a student reading this book by Steve Weinberg, and the sentence I went back, it reminded me of this very much. Often the way it is in physics, our mistake is not that we take our theories too seriously, but we do not take them seriously enough. And I think there is actually great truth in that. And I was guilty of not taking some of my own work seriously enough, because I think the answer to this lies in work that is almost 2 decades old. How is it that S and omega care about each other so much? That's a strange marriage, entropy and angular velocity. Why is there... So why maybe it's actually not a marriage, because they're actually looking in opposite directions. But in any case, there's some emotion there. There's a bond.
Maybe it is.
I'll get into that.
I won't touch that one. To answer this question, we need to understand something about the dynamics. I haven't given any discussion yet about what a possible dynamical coupling between S and omega might be due to. And we need to take into account the stability of rotating, stratified, and magnetized plasmas, even if they're weakly magnetized. And we need to take rotation, stratification, and magnetism all seriously on the same footing. So, before I get into too much heavy overhead with the equations, let me give you the punchline, which is in 3 parts. Number 1, counteralignment of the entropy and angular velocity gradients is in fact a rigorous condition for the marginal stability in a rotating convective magnetized gas. That's kind of a 1-sentence summary of what the connection is.
It's quite surprising at first sight, because you've got a statically stable polar region. You've got a positive n squared value, which is the opposite of what you expect from simple straight convection, right?
That's right. But here it's the rotation, when it's folded in, allows you to be marginally stable even with a positive n squared near the poles.
Right, it's what we meteorologists call sloping convection. There's another direction on which the fluid can slide.
Interesting. Okay. So the solar rotation profile can be understood, or at least I'm claiming it can be understood as a consequence of maintaining a state of marginal, I've been calling it marginal stability, but it's really marginal instability, to the most rapidly growing axisymmetric, and we mustn't forget the non-axisymmetric dynamical modes as well. A magnetic field is essential to understanding why this is true. So let me give you a quick run-through on the linear response of a magnetized medium to incompressible disturbances. I'm always going to be working in the Boussinesq approximation here. So here is my dispersion relation for Alfvén waves. K is the wave number, VA. I should have written down, it's simply the Alfvén velocity, B over mu naught, square root of rho. And I've written it in this funny way because, in fact, there are 2 distinct modes present, the so-called Alfvén mode and the slow mode. And within sort of the Boussinesq approximation, these 2 are degenerate. But that degeneracy will soon be lifted as I include more complexity in the problem. So think of this as sort of, this is going to be a Darwinian evolution of the equation. I'm going to start off with the pre-Cambrian form. It'll be very primitive and simple, and then it'll sprout kind of successively more complicated terms as we get to where I want to go with the physics which is relevant to the solar interior. So I expand this and I have a simple looking quartic equation, a quadratic in omega squared. Now if I go from this step to the next step, adding rotation to the system, then I get two terms that appear. The first of these is epicyclic. I guess in the fluid community people call that the Rayleigh discriminant. But the epicyclic motion is simply the response of inertial waves. If I have a rotating fluid and I perturb it somewhat, if I give it a kick, then the orbits will oscillate radially back and forth. It's exactly the reason that circular orbits turn into elliptical orbits in Keplerian motion if I make a small disturbance from a circular orbit. And that by itself is less interesting in terms of the dynamical response. It simply kind of adds to the Alfvén response. But then there's a second term here which is kind of shows the effect of what I call tethering. And this additional piece, you can obviously see in a mathematical sense, allows the possibility for an instability to be present if d omega squared d log r is decreasing outward. Here I'm just doing the equation assuming omega is a function of cylindrical r. So this is what gives...
Magnetic field geometry, is this some completely uniform field? Or is
You
it
see, I'm going too fast. It doesn't even matter what the magnetic field geometry is.
But you are assuming it's uniform, aren't you?
I am assuming it's uniform on the scale of the wavelength.
Like small scale.
WKB. It's a WKB approximation. But in fact, I'm assuming only, this is an axisymmetric, so I'm assuming that there is a K dot VA, which means at least I need a poloidal magnetic field to be present. In this form of the equation, actually, let me be a little bit more careful. I'm assuming here, I get an equation which looks like this if I have a KZ present. So I have a Z component of K. If K is not along the axis, there's a trivial modification, which I'll do in a moment. So I'm assuming I at least have a Z component of the magnetic field present along the rotation axis for this equation to be valid. More generally, the instability is present whatever the geometry is, provided you have some poloidal field. If you allow non-axisymmetric perturbations, then you don't even need that qualification. So just in case you haven't seen it, here's kind of a cartoon picture of the magnetorotational instability. This is what that final term is doing. The K dot VA squared is acting like a restoring force which is proportional to the displacement. So it's as though I have two fluid elements or 2 point masses that are connected together by a weak spring. And for those of you who haven't sort of grown up with the MRI, the basic reason that you get an instability is that, let me go back one little step. Here I have my rotation center. I have a fluid element orbiting like this. My fluid, another fluid element a little bit farther out. The magnetic field, which is kind of threading these fluid elements, acts like a spring connecting them with a restoring force proportional to the displacement. I get a torque pulling back on this mass. It tends to drop to a lower orbit. On the other hand, I get a torque speeding this mass up. It acquires angular momentum and moves farther out, and so that initial disturbance gets larger. The fluid eventually mixes, and this has now been studied for many years. So it's that second term which is responsible for all the action. So continuing with our evolution, I write the same equation in a more compact form. So I'm introducing this variable omega bar, or curly pi, or whatever you'd like to call it, which is omega squared minus k dot VA squared. I take the next step, which is to put in more general wave numbers and introduces only this geometrical factor of k squared over k squared z. I allow now a more general form for omega, so instead of kappa squared, I have a slightly more complex operator here involving both gradients, axial as well as radial. And then finally, I look at the final form of my equation when I include the effects of an entropy gradient depending upon R and Z. I get another term which simply adds together with the kind of generalized Rayleigh discriminant for the rotation. So this is an equation whose stability properties can be analyzed rather straightforwardly. And one can also see the interesting result that the presence or absence of a magnetic field makes a huge difference to this equation. To analyze the stability, this is an equation where one can pass smoothly through the limit omega squared equals 0. If I have no magnetic field whatsoever, do the bottom case first, the k dot VA squared terms vanish, and I simply have these two pieces to contend with. And so this is the formal criterion for hydrodynamical stability. On the other hand, if I have a magnetic field present, then I retain all the terms which are proportional to k dot VA squared. And it turns out that the criterion for stability in this case looks very much like the hydrodynamical criterion, but it has this big 4 omega squared as well. So it makes a huge difference whether VA is 0 or whether VA is finite. In principle, at least mathematically speaking, even infinitesimal, because the magnetic field never enters into the analysis by itself. It's always the magnetic tension, k dot VA squared. So if VA is small, it simply means you have to go to bigger wave numbers in order to get significant magnetic tension forces. And if there was no dissipation in the problem, you could have any finite value of VA causing instability in this way. In practice, of course, in real systems, you run into dissipation scales if you have to go to very, very small wavelengths. This can be perhaps more clearly written if I use not the wave numbers, but the displacement vector. So this is a funny way to write a dispersion relation. I have a k dot VA here, but instead of these funny operators, if I write those entropy response and the rotational response in terms of my displacement vector, so n here is a unit vector along the direction of the displacement, then the criterion for stability can be written in a way where the gradients themselves appear directly and explicitly. And you can now see why it is, I think, intuitively, that when you're at marginal stability, the angular velocity and the entropy surfaces have to coincide with one another. You need to have n dot grad vanish simultaneously in order to get this marginally stable response. And basically a disturbance in a plane of constant omega, if it coincides with a plane of constant s, will give you this marginally stable response. One can do a rigorous analysis, and actually priority for this belongs to Professor Papalouizou, who first showed in 1992, not using this kind of a technique, but by using a powerful variational technique, that the basic criterion for stability for a rotating, magnetized, stratified gas under very general circumstances, where the only symmetry you're assuming is axisymmetry, is this criterion here, which is essentially the cross product of omega and the entropy has to have a certain sign. I've indicated in the solar models how this would be satisfied if I put a 0 over here to look just at the marginal case. The first two terms in this analysis tend to be positive. The second two terms tend to be negative. There's a secondary requirement as well, but it's less interesting. It's amply satisfied for the problems we're interested in. So have we missed something? Whatever happened to good old-fashioned convection? Well, to really pick out the truly convective modes, I need to go to non-axisymmetry. So if I look at an e to the im phi, and I'm cheating here a little bit. If I'm doing a local analysis which is non-axisymmetric, in fact, I really have shearing coordinates that I have to worry about. So this equation is strictly valid only in the case of uniform rotation. But it illustrates the coupling, which is the important point here, and which is true, which remains, the coupling retains its form even in a more complicated problem. And you see that the n squared appears by itself coupled to the non-axisymmetric modes. So to ensure stability both to rotationally induced modes and to convectively induced modes, I need to make sure that both the axisymmetric and the non-axisymmetric instabilities have been marginalized. In one case by making n squared very, very much smaller than its nominal value. Of its nominal value would be the free fall time. So it's much, much smaller than that. And the other modes, the axisymmetric modes, are marginalized by making omega and s be very nearly counter-aligned. With even weak magnetic fields, axisymmetric modes become major players. When we had no magnetic fields in the analysis, the axisymmetric modes were much less important to worry about because they involve angular momentum, not angular velocity gradients.
Without that equation, can I just ask?
Sure.
Are you taking the simple case of uniform rotation just to let us off having to look at a much more gory dispersion relation, or haven't you done that yourself?
Well, I've done it myself.
You have. So
Yeah.
it still works. The m squared n squared term still is stable.
There are other terms as well, but the basic, and that is exactly, that's the potential danger for stabilization, or for destabilization. In fact, you don't even use these coordinates. The way I like to do it is to go into shearing coordinates and to write it as ordinary differential equations in time rather than a modal analysis. So all of that's been done, and yes, I'm sparing you all of the horrible details, which I'm happy to go into in my notebooks if you would like to see. So quick summary. Z is up, radially outward is this, an entropy gradient which points like this, and an angular velocity gradient like this. This corresponds to kind of the solar case, and this would be marginally unstable. A configuration like this, or a configuration like this, and this actually looks like, I have it in terms of angular velocity, but an angular momentum gradient would actually look more like this. It would resemble this kind of a configuration. These are two stable, hydrodynamically stable configurations.
Which one would be more like Taylor cell, Taylor column? The two on the right.
Well, then it would be just in the rotation. The angular, it would be, I guess, something closer to this with the angular velocity would be along the radial direction. This is what it looks like in more detail. What I have a plot here is for solving for what the critical unstable value of k dot VA squared is as a function of the displacement ratio psi r over psi z. And very near marginal stability, you have an unstable zone which is just hidden down there. Right at marginal stability, this comes up and just kisses the x-axis, the abscissa, and comes down. And you have just a few unstable modes in this very small value of k dot VA. In other words, they tend to be pushed to longer wavelengths. And presumably it's being pushed to wavelengths which become of order the relevant coherence size scale for the magnetic field, at which point the instability shuts itself off. So this is how this instability regulates itself. It pushes the angular velocity development and the angular velocity gradient to such an extent that it has to go to ultimately the largest wavelengths available to it to sustain the profile.
That wavelength is across your contours, isn't it? Because the displacement's along them, more or less, in that zone.
It depends where you are.
But I thought that you were telling us the direction of the displacement. Surely that's more or less along the omega and say S contours.
That's right.
So the wavelength is across that. So you've got quite a lot of room.
You have quite a lot of room. And those are the long wavelengths ones which are actually involved in the instability itself. Let me just remind you of why it is plausible that a magnetic field can sustain some degree of coherence even as highly developed turbulence is going on in the background. These are old movies by now, old home movies from John Hawley, one of the first global simulations of magnetorotational modes for an accretion disk starting off with a constant angular momentum torus. And what I wanted to convey here was that even though you have highly convoluted and quite fully developed turbulent flow, as many of the numericists in the audience will know, the MRI can still retain extremely vigorous growth. And in fact, most of the energy in these kinds of simulations in the magnetic field is dominated by the largest scales. So I emphasize this because the sun, which is, if it's not rotationally dominated, it certainly has a major rotational component. And the fact that the background flow is turbulent is not something that is necessarily going to wash out the magnetic effects, which is an argument that I sometimes hear. You can have coherent magnetic response even in the presence of highly developed turbulence. So let me summarize and give a synthesis. One, a dominant balance coming from the vorticity equation corresponding to a thermal wind balance seems to hold in much of the solar convective zone. If I assume this dominant balance, then one can easily show that ds d theta is significantly larger than the logarithmic gradient in the radial direction. And this anisotropy in the theta and r gradients is seen directly in the omega contours throughout much of the convective zone. This thermal wind equation can be solved exactly with the assumption that S is a function of omega, that entropy and angular velocity surfaces coincide. And this produces isorotation contours that seem to be, at least in broad agreement, with the helioseismology data. As it happens, the relationship that S is a function of omega, that surfaces of entropy and surfaces of constant entropy, surfaces of constant angular velocity, coincide, this corresponds precisely to the marginal stability requirement of axisymmetric, baroclinic, magnetized modes in a rotating gas. And I don't think it's a coincidence, to answer the question that I posed. Non-axisymmetric modes coupled to n squareds, they tend to be less sensitive to magnetic couplings. Axisymmetric modes couple strongly to the rotation, and their stability is much more sensitive to a magnetic field. A hydrodynamic stability criterion is very different and nowhere near criticality, which I think is the main reason why people lost interest in it. The big idea, the major point I would hope to get across is that the gross dynamical features, Batman isotax, it sounds kind of cool, and the thermal adiabats of the solar convective zone are a consequence of marginalizing the dominant magnetobaroclinic linear unstable modes of the system. Why hasn't this been seen in the simulations? Some of the simulations have in fact been magnetohydrodynamical. I haven't been involved closely enough with those simulations to give you a truly authoritative answer, but I suspect that they're not resolving the fastest growing modes. You need to resolve modes with kVA squared of order d omega squared d log r. And this corresponds to wavelengths which are perhaps 10 to the minus 3 r. for nominal solar values. So these are quite small. And I suspect that in the simulations, indeed, those magnetic modes may well have been washed out. I think it's possible that one can surely fudge the parameters. One can change the parameters and do a proxy problem, which is not identical to the sun, but which has the same qualitative features of the sun, that will bring these modes into a not easily, but more easily computable regime. And it is absolutely essential to take the codes and calibrate them with a linear dispersion relation to make sure that at least in idealized problems where you expect a clean WKB response, that you actually see it in the code. The ideas, I think, are, as you see, they're generic, they're very simple. I haven't tried to do, at some level, the more complicated problem, where I would have to worry in detail about what is going on with the flows, with the Reynolds stresses, Maxwell stresses. This is a very simple picture. And so for the future, my hope is that these ideas will prove to be useful for problems that they were not designed to solve directly. Mike McIntyre had the interesting idea that he communicated to me just recently, that perhaps the latitude dependence of the dynamo cycle, the fact that it tends to occur more favorably along equatorial latitudes rather than polar latitudes, may be related to the fact that the entropy stratification is stable at higher latitudes and more unstable at low latitudes. So I don't know if that will play itself out, but it's an interesting idea and the sort of example of the kind of problems that we may start to be able to make progress on if these ideas hold up. And I think that's a good place to stop.
Good. WKB, full field approximation. Is what you mean that we're basically just assuming that the magnetic field has a dipolar structure?
No, nothing so global. It simply means that on the scale of the wavelength of my perturbation, the magnetic field is more or less uniform.
It doesn't matter which direction it's pointing at all. It's just that's sort of the extra
As long as it has some
spring
component.
term.
That's right. As long as it has some component along the wave number. It doesn't matter. The details do not matter. I'm sorry, I guess Dave.
I mean, it's very appealing. But, I mean, if you think you'd have convection, suppose you had no magnetic field, you'd have convection, and it would come to some horrible nonlinear state because of the Reynolds stresses, whatever. Then let's say you introduced a field, and it's almost certainly a dynamo. So it's going to be a horribly messy dynamo with field all over the place, right? Changing direction on very small length scales. And then that's going to saturate for some reasons of its own. But you would say that it would saturate to kind of become marginal for the MRI. But dynamos could saturate for all kinds of reasons. It doesn't have to saturate like that.
Well, if I don't know that dynamo theory is developed enough that it's a compelling argument that the field is just going to be dominated by the smallest scales and there won't be any coherence for the MRI to work. I think in a real system that it doesn't work that way. That is to say, you don't start off with a demagnetized star, let convection run, and then nature puts in the magnetic field. I suspect that it is there from the moment it is born, and one of the reasons that marginal stability is important is that it has grown up all of its life, so to speak, in a marginally stable state. I suspect it's sort of been there from the very beginning. I don't doubt that you could construct scenarios where you keep the magnetic field away, you let the thing convect and then add it in and then have things go wrong. But I think in real systems, it is a more conservative assumption to allow the magnetic field to be there from the very beginning and to have the system sort of evolve.
More than the minimum, it probably wasn't there, actually. In the Maunder minimum, it probably wasn't there. You say it's been there all its lifetime. It might not have been there in the 17th century.
I have no answer to that.
Can I just ask a follow-on question and then get to Mark? So, I mean, the magnetic field's critical for everything you've said. That's why the omega rather than
Yes.
the gamma is important. The L is important. But, following on from David's point, I mean, you've got the solar cycle, you've got the 22-year solar
Yes.
cycle, so you've got the magnetic field changing its intensity and the ratio of toroidal to azimuthal and so forth. Is there any indication that the lines of constant angular velocity, the iso-rotation lines, change during that cycle?
I'll defer to the experts, but I think the answer is no. I think the gross features are more or less the same. Michael, do you have a better answer?
Well, what I was going to say is that everything we've been learning about the sun over the last 10 or 20 years seems to say that high latitude dynamics is one thing and low latitude is another. And this, if this proposal is correct, it will be underlining that point because of the static stability being positive, the n squared being positive in high latitudes and negative in low latitudes. Now, there might be a reality check on that one could conceive of, mightn't there? Namely, if you say that if you extend this proposal a little bit to say, right, in high latitudes it's statically stable, so the only sort of convection mode available is this sloping convection, which very much feels the magnetic tethering, whereas in low latitudes it can just punch through vertically because it wants to be statically unstable anyway. Then a reality check might be to look for, azimuthal streakiness, zonally symmetric streakiness or spirals in high latitudes, a bit like the spirals you see in the accretion disks when the MRI is going. Yeah, is there any data, do you think, that might look for patterns in polar latitudes in the sun that look azimuthally streaky?
Patterns of what variable, you think?
Well, I don't know,
Density?
maybe temperature or maybe just, you see, well, magnetograms probably. If there are streaky magnetic features, perhaps they'd show up in the magnetograms. Does anyone know what polar regions look like in the real sun?
Polar regions are pretty inaccessible.
No, I've never seen it.
It's not
Picture.
been observed, has it?
No.
The Ulysses, that was sort of...
Even omega near the poles, the diagrams are kind of extrapolations.
Magnetograms of the disk certainly don't show streaks and all.
But they are all seen from the equatorial plane, aren't they?
Because you can't measure the horizontal speeds very well at all with the magnetogram.
So we need to propose a mission for a polar orbiting magnetogram instrument, I think.
I think that would be a good.
I think, well, yeah, there are missions in planning to do things very much like that, to look at polar data from the sun.
Wasn't there something called Ulysses that looked at the solar wind in a polar orbit?
Sounds
Remember
familiar.
that correctly?
Yeah, but that's solar wind. It's not.
Yeah.
It's too far away. It
Yeah.
didn't. It couldn't see the
Right.
sun's disk in detail, could it?
Well, it was particle detector,
Right.
different kind of instrument.
Any other?
You solve the exact thermal wind equation, or did you neglect the first term on the right-hand side finally? I didn't follow.
I dropped the term which was proportional to dp d theta.
And can you check a posteriori that this is?
Oh yeah, that's a tiny term. That just depends upon the oblateness, and that's sort of second order in the oblateness, so it really is an excellent approximation. The thermal wind equation, the derivation of the thermal wind equation was done before me. That's not original with this work. The solution is something else, that's original, but the equation itself was there before.
It takes a lot to disturb thermal wind balance. It's like pushing a huge weight, trying to hold it off vertical.
Yeah.
It's-
Perfect.
I feel like I should already know the answer to this, but I don't know much about the MRI. I think you mentioned that the axisymmetric modes require a field component parallel to the rotation axis.
No, not necessarily. The axisymmetric version of the MRI simply requires a poloidal component of the magnetic field. Principle could be locally purely radial as well. But you need K dot B to be non-zero. And if K has only an R and Z component, then B would have. But the MRI is even more general than that. In fact, when people do numerical simulations, one way to control the MRI is you put in just a pure azimuthal magnetic field. The MRI is still present, but it tends to have somewhat smaller growth rates than the axisymmetric version. But it's the reason it's such a powerful and important instability is that it is precisely because it's independent of basically of field strength and field geometry.
Gradually, then they change. And as the field gets weaker and weaker.
Yes, there are limit. Well, everything that is assuming I have an infinite medium, and I'm always an ideal MHD. When the field gets weaker and weaker and weaker, then the fastest growing wavelengths are actually damped out. And then you're still unstable at the longer wavelengths, but then they have very, very long growth times. Conversely, when the magnetic field gets to be very strong, any wavelength that would fit inside your system would have a reactive response. And the wavelengths that would be unstable wouldn't fit inside your system. So at that limit, it breaks down as well.
I mean, as a footnote to that, couldn't we kind of focus a bit more on your marginal modes in high-ish latitudes? And their wave numbers are kind of pointing toward the pole. They're more or less horizontal. They're almost horizontal because your contours are
The displacements
almost
are
vertical.
Yeah.
So the displacements are vertical, but the wave numbers horizontal,
Other way
pointing toward the pole, isn't it?
No, near the poles, the unstable modes would. No, you're right.
Let's say it's
The
60
displacements
degrees.
would be vertical, and the wave numbers horizontal.
And the magnetic field that needs to be effective is actually a magnetic field in the horizontal poleward, aligned horizontal poleward. And if you now think of the sun's dipole field, I mean, the ordinary dynamo cycle is providing a field a bit like that, isn't it? And we know it comes out of the pole and dipoles around in space, don't we? So there's probably a fair horizontal component inside the convection zone, isn't there? And that's exactly what you need.
So, yes, I don't argue with that. Sounds good to me.
It wouldn't matter if it reverses sine every 11 years.
No,
Work just the same.
K dot BA squared.
How does magnetic field influence your thermal wind?
That's a good, this is an example where the magnetic field is important for the small scale instabilities, but in terms of the large scale gradients that appear in the thermal wind equation, it's actually negligible. The same thing happens, or at least you'd have to be, I think that's a reasonable working assumption. It may break down, particularly near the tachocline where the magnetic field can get substantially stronger. But when you do accretion disks, you also make a similar assumption. The actual rotation profile is Keplerian. The magnetic field has very little influence on the hydrostatic equilibrium, but for the stability, it becomes much more important.
And the large scale dipole field has
It's locally it may. It can be, you can get fields of several thousand Gauss, at which point sort of near a sunspot or something like this. And in those regions, I couldn't apply this theory directly, but the broad hydrostatic equilibrium of the magnetic field of the sun, in that context, the dipole field is really quite weak in the convective zone. It's not much stronger than the Earth's magnetic field on average, maybe a few Gauss. Yeah, there's no great difference between, as far as I know, between the azimuthal and poloidal field.
I mean, there's a kind of clear theoretical reason for all that, isn't there? It's like having a bunch of concentric flywheels connected by spider webs, sort of, isn't it? And they're all spinning happily and stably in terms of, hydrostatic and inertial instability and so on. It's simply that their angular momentum is being changed systematically by the spider
Right.
webs, sort of.
It's being drained. Yeah.
Which
Just a
brings
smaller
up
force.
my understanding was that the MRI requires some sort of thermal convection to get an eddy diffusivity into the problem to get the angular momentum to gradually go out.
Well, absolutely not.
Absolutely not.
Yeah, in fact, thermal convection in accretion disks does exactly the opposite of what you want it to do. No, in the MRI, the angular momentum transport is a feature of the linear instability itself. The Maxwell stresses, even in the linear domain, are pulling angular momentum outward, and it retains that in the nonlinear development. So there's no...
There's no place where you need a...
There's absolutely no place where convection is needed.
There's no place where... What about a enhanced eddy viscosity?
Well, convection and
No, just in the MRI, do you need reconnection?
people know,
If you have
I'm not-
reconnection, you have to have some sort of enhanced,
what you have are forces. What you have are correlated fluctuations in BR and B phi.
yes?
Those are the actual stresses that appear in the equation, and so those are the ones I like to work with and to think of. And those are always draining angular momentum outward. Whether they can be formulated as an effective eddy viscosity or not is sort of beside the point. The torques themselves are present, and whether you need to think of it as an eddy viscosity or as a secondary consideration, the mathematics speaks for itself. The stresses that you need.
So the MRI doesn't depend on convection in your point of view, and it doesn't depend
no,
on...
not just mine. It really doesn't depend upon convection.
And it doesn't depend on reconnection events?
The MRI itself does not depend upon reconnection events, although certainly in the fully developed turbulent cascade that will be present when the MRI does its thing,
Yes.
reconnection will be an important piece to the overall puzzle, and it's part of the saturation mechanism. But the instability
okay.
itself doesn't depend.
I think maybe you should finish
We'll,
that over
we'll
a cup of
continue
coffee.
it.
I have to be gone for a while. I've got lots of questions, but I'll keep them for
Okay,
upstairs.
good.
So we should thank